Hello, and thank you for viewing this presentation, PIC Microcontrollers and dsPIC Digital Signal Controllers, a quick overview. This video provides a high-level overview of the PIC MCU and dsPIC DSC architectures, focusing on the basics, and is intended for users who are new to these products or microcontrollers in general. During the course of this presentation, we will discuss the following. We will take a look at the basic architecture that makes up all PIC microcontrollers and dsPIC digital signal controllers, the Harvard architecture. All of Microchip's products use this fundamental architecture as its foundation. We will also relate some of these features to Microchip's product map. Finally, we will discuss some common peripherals that are needed. Shown here is an overview of Microchip's entire MCU and DSC product portfolio. These products range from the very low cost and tiny baseline products through to our dsPIC digital signal controllers that are basically a microcontroller with DSP functionality, up to our high performance PIC32 family. Note that as you move up and to the right, these products will have more features and provide faster performance. All of these products share some fundamental similarities. Let's take some time and discuss these. Shown here is a simplified block diagram of the basic components that make up any PIC microcontroller or dsPIC digital signal controller. The central processing unit, or CPU, does all of the arithmetic and logical operations that are required during the course of the microcontroller's operation. Any input received or output transmitted from the microcontroller on its pins are under the control of software instructions written by you, the user, and stored into program memory that tell the CPU how to use this information, or how to think. Also note the oscillator shown here. This component can be thought of as the engine for the MCU, that is the clock source used by the entire system. Here, the oscillator is shown as an integrated part of the chip. However, PIC microcontrollers and dsPIC digital signal controllers also feature the ability of using an off-chip oscillator, such as a crystal, if the user wishes to use one. If we look at the on-chip memory, these products take advantage of what is known as the Harvard architecture. This simply means that this microcontroller, or digital signal controller, has two separate memory locations, one for program memory that will contain the code or firmware that you will create to tell the microcontroller how to behave, and the second memory location, the data memory, that serves a couple of purposes. First, data memory will be used as a sort of scratch pad for the CPU, holding information for use at various times during the course of operation. For those of you familiar with any type of programming language, this is where such components of your software such as variables will be stored. Secondly, data memory plays an important role in configuring and communicating with the peripherals on the device. This won't be discussed here. However, any product will have a datasheet that serves as a user's manual, which details configuration and peripheral usage. Note that each memory location has its own connection or bus to the central processing unit. The advantage here is that information of different widths can be transmitted to the CPU separately on its own bus, with information moving into or out of the CPU to these locations simultaneously. So what does this mean? Let's start with program memory. Each memory location, including program memory, will be constructed of a number of registers, with each register residing at its own unique address. Each program memory address location will contain a series of bits that represent some unique instruction to the central processing unit. Remember, this is a digital being that speaks in binary, or what is known as machine language. So if we would like the CPU to add two values, multiply, or store a constant somewhere in data memory, a unique series of bits will be sent from program memory that holds the program you developed. Now shown here is a 14-bit value or instruction word at each memory location. This is found on Microchip's mid-range microcontrollers such as our PIC16 products. If we look at Microchip's MCU and DSC family roadmap, as you move up and to the right on the map, program memory sizes at each register address increases. This is one of the advantages of using the Harvard architecture. By using separate memory locations for both program and data memories, we can make use of a long instruction word, or more bits for each instruction. This allows us to get as much information to the CPU at one time, thereby speeding up code execution, which could be very important to your application. Let's now take a look at the other memory location space, data memory. Data memory is typically used by the CPU to store such things as runtime variables that will be used again at a later time for other operations, so sort of like a scratch pad. Shown here is an 8-bit wide data memory. Each bit will be either a 1 or a 0, and each 8-bit location or byte will have some significant meaning to the central processing unit. Perhaps this represents a numeric value from a previous operation, or some specific information concerning one of the peripherals. Not all PIC microcontrollers have an 8-bit data memory location, and this is what differentiates our various product groupings. Note that each product is categorized into families that are determined by the size of the registers in the data memory. So if you hear something about 8-bit, 16-bit, or 32-bit microcontrollers, they are referring to the number of bits available at each register location in data memory. One thing to keep in mind here is that program memory is non-volatile, while data memory is volatile. This means that when power is removed from the microcontroller, anything in data memory is wiped out. So if you stored the result of a mathematical operation from the CPU into data memory, once power is removed from the MCU or DSC, this data is gone. Program memory, on the other hand, will remain intact once power is removed. Therefore, once you have programmed the microcontroller with your application code, this memory remains unchanged until you program it again. Let's talk peripherals. Remember, this is how the microcontroller communicates with the outside world over the pins and vice versa. Each microcontroller will come with different peripheral options that you can select to best suit your application. Here is a list of some common peripherals. As you can see, depending on the application at hand, Microchip offers a wide variety of peripherals that can be used to communicate with the CPU. Analog peripherals convert analog signals into digital signals. Communication peripherals are designed to make life easier when developing such applications for USB, Ethernet, etc. Other unique peripherals include capacitive touch sensing modules. The whole thing to remember with peripherals is that they are intended to integrate features onto the microcontroller so that you don't have to add these to your circuit in the form of additional external or separate chips or components. This helps reduce the overall size and cost of your circuit. Furthermore, peripherals are intended to make development a lot easier by having certain operations perform automatically rather than you needing to develop code to accomplish the same result. So we've discussed the basic components of a PIC microcontroller and dsPIC digital signal controller and showed you some simple block diagrams. But what does this really look like? If we were to remove part of the plastic packaging that protects the microcontroller and magnify what's inside, it might look similar to this picture shown here. You can see the tiny connection leads that surround the microcontroller and connect such components as the peripherals to the pins on the device. In the lower right-hand corner, you can see the circuitry that makes up the central processing unit, or CPU. Program memory is over here on the left. Data memory immediately above that. And here are the peripherals that are included on this particular part. Communication peripherals such as a USART and I2C SPI module. A capture-compare PWM module that is commonly used in motor control applications. A timer that can be used as a time base for your application, and finally, an analog to digital converter for translating analog signals. Note that this particular device does not have an internal oscillator. So let's summarize what we have covered. Each device in Microchip's PIC and dsPIC product portfolio use the Harvard architecture as its basis, using a separate bus for each of its memory locations. Products are categorized as either 8, 16, or 32-bit families, which corresponds to the size of each register location in data memory. Program memory word sizes, or the number of bits in each register location, will also vary amongst products. The bigger the word size, the more information that can be passed from program memory to the central processing unit at a given time. We hope that you found this presentation introducing Microchip's PIC microcontrollers and dsPIC digital signal controllers useful. To comment on this presentation or anything else, please contact us at academic@microchip.com or visit the Academic Program homepage at www.microchip.com/academic.